So we've seen reactions that alter the carbon skeleton and how they're really important in synthesis. And we've seen how helpful retrosynthetic analysis can be when designing a multi-step synthesis. Our discussions about these topics have been rather limited because we've only covered two reactions that can alter the carbon skeleton. So what we're going to do in the next couple sections is introduce additional carbon-carbon bond forming reactions and their mechanisms, and expand our ability to perform these retrosynthetic analyses. And that means then that we can design more sophisticated synthesis. As mentioned in the previous screencast, the new reactions that are introduced in the next two sections are all related by their mechanisms. They're all going to be nucleophilic substitution reactions. Similar to the ones that we've been studying thus far. And my suggestion is to pay attention to the patterns that emerge in the mechanisms. And this is just going to be my suggestion all the way through organic chemistry, right? Is to pay attention to the patterns, because if you can group reactions together by patterns, it's just going to make learning organic chemistry a lot easier. So the more that you focus on the mechanisms, the more simplified organic chemistry is going to become for you. Now, in section 10.7 or chapter 10, we learned that nucleophiles can attack epoxides to open the ring and produce substituted alcohols, right? And so we see this here. This is something that we've seen before, where we know that that's a spectator ion. So OCH3 acts as the nucleophile and it attacks one of the carbons and the ring opens. And now, of course, we have an alcohol functional group here. We can also use epoxides to form new carbon-carbon bonds. So for example, a new carbon-carbon bond can be formed when a carbon nucleophile, like the cyanide here, is used to open the epoxide ring. So this is a cyanide anion, right? And so we form a new carbon-carbon bond. That's a new carbon-carbon bond forming reaction. So let's look at this a little bit more in depth on the next slide, and specifically look at the mechanism for this. So when we look at this slide, and what we see happening here is we have a terminal alkyne, and we're going to use a strong base to deprotonate this. And then we are going to use an epoxide to form a molecule. So we're going to increase the number of carbons in the molecule, but now we're going to have two functional groups. We're going to have an OH functional group, and then we're going to have this triple bond, the alkyne functional group. I want you to notice the third step here is an acid workup. This is using one of our strong acids and water. So let's look at the mechanism for how this progresses. And this is really combining a mechanism that we've already looked at. Okay. So the sodium hydride leaves us with just a hydride ion, right? The sodium is a spectator ion. It's going to come out, it's going to steal that proton, and those electrons are going to go back on that carbon. This is a proton transfer step. Okay. And here, right, we end up with a carbon ion. Now it will undergo an SN2 reaction with the epoxide. Where the electrons will come in, they'll attack one of the carbons in a ring opening, and the ring will open this way, and that's an SN2 reaction, right? And when that occurs, we end up with a deprotonated alcohol. And that's when we do the acid workup to make sure that we can protonate that so we don't have a charged species. So these electrons go here, those electrons go there. And now we have an alcohol functional group and an uncharged product, which is what we want. Water, of course, is the byproduct there. Okay, so this is not the only way to create a new carbon-carbon bond. As we mentioned, we're going to learn a couple different reactions. And the next series of reactions we're going to learn are looking at organometallic compounds. Now, as a reminder, organometallic compounds are going to be compounds that contain some sort of metal and this organic group. The metal here is more electropositive, and so it ends up where the carbon here then has more electrons on it. And so a lot of times it can be represented as just whatever the R is negative. So like in this case, it would be CH3, CH2, right? And actually, I think I want to do it like this so it doesn't show the... because the electrons there are on that carbon. So that's how it can be simplified. So basically, the organometallic reagents behave as carbon nucleophiles. And the lithium one that you see here is a common one. And so they're going to react then with the epoxide to open up the ring, okay, and form a new carbon-carbon bond. So when that ring opens, then we also have we have an SN2 reaction, and then we also have a proton transfer, and we end up with an alcohol. Let's look at another organometallic compound. Let's look at a Grignard reagent and the mechanism for this. Remember, the Grignard reagent here is shown in red. Remember, Grignard reagents are MgCl. A lot of times will clue you in that that's a Grignard reagent, and Grignard reagents just act as carbanions. So we can shorten and draw that Grignard just like that, okay, where we drop off that magnesium chloride, because the magnesium there is much more electropositive than the carbon, and so it leaves kind of the electrons there, if you can imagine, on that carbon. So it's going to react through an SN2 reaction with the epoxide here. And so what we're going to see happen is that these electrons are going to come and attack that partially positive carbon. Those electrons are going to jump back up there on the oxygen, and that's going to open up the ring. Right? And so we're going to use our arrows to help us see where we're going to have bonds, right? And so 3 minus. Now, I always personally just like to count a lot of times. And so I'll be like, okay, hey, look, that's 1 and 2. And so then we come over here and there's 1 and 2. It just helps me double check that I didn't accidentally throw a bond in there, because sometimes it's hard to keep track when you're forming bonds. But I also want you to be able to visualize here that this is the bond that purple arrow is showing, right? And then we have 1 and 2. So make sure that you can visualize this. The more that you can visualize, the easier that organic chemistry is going to be. Now, we can't have a charged species hanging out. So we notice we have step 2, that's an acid workup. And so we're going to come in here and we're going to have a proton transfer. And we're just going to show our generic acid as H3O+. Where those come in, they grab that, and those go back there. And now we have our alcohol functional group. We have synthesized here 2-phenylethanol. 2-phenylethanol is found in the extracts of certain flowers like roses and carnations and geraniums. And so that makes it really useful in the perfume industry. So this is something that if you were to go and work in cosmetics, you would probably end up synthesizing, and you could synthesize it through an SN2 reaction with an epoxide. So we went to France a couple of years ago, and it was really neat to tour the perfume factories because they did do a lot of organic synthesis to synthesize fragrances. So it is a kind of hopping area of organic chemistry. So as we've discussed all along in this chapter, carbon-carbon bond forming reactions are really valuable in organic synthesis. They help us make bigger molecules. And so to know whether one of these reactions should be considered for a synthesis, we need to recognize the feature that characterizes each of the products, which is the bonding arrangement of the form here, where it's the carbons 1, 2, 3, and then you can see the OH group there. Notice, right, that they've got these numbers here for you, and the bond between carbon 1 and carbon 2 are the ones that are formed through the ring opening reaction. So notice that pattern. Carbons 2 and 3 have to come from the epoxide, right? And so remember, we're looking at transforms here. So these would be the product, and we're thinking about how we could synthesize it. And these two things could be used to synthesize it. So let's do a problem like a problem that you would see. Okay. And it says, show how to synthesize the molecule below, beginning with compounds that contain 4 or fewer carbons. Now, when I look at this, I say, okay, I need to start from 4 or less carbons, okay, to make that. I come over here and I go, okay, there's 1, 2, 3, 4, 5, 6, 7. This guy has 7 carbons. That leads me to believe that I'm going to have to use a reaction where I am going to increase the carbon chain, right? So I'm going to use one of the reactions that we've learned where we can increase the carbon chain. The other thing that I notice is we have an alcohol functional group here, right? And so that, a lot of times for me at least, is an indication that maybe we could use one of these epoxide reactions, okay? And so now I go down to the think questions that have been given to us. Does the target have the bonding arrangement carbon, 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 OH? And the answer to that is yes, and there are actually 2 of them. So I'm going to highlight those 2. So let's highlight one in purple. So one is carbon, 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 OH there. And then the other one, which let me highlight in yellow, would be carbon, carbon, OH there. So we have 2, okay? And so the next one says, how can we apply transforms to undo the existing epoxide opening reaction? And I don't have a lot of space there. I didn't give myself a lot of space, but there's 2 ways that we can do this, right? One of the ways that we can do this is if we're looking in purple there, then it's 1, 2, 3. And we can look at that and we can say, okay, hey, look, I know the 2 and the 3 there for the alcohol, where the 3's on the alcohol, that 2 and 3 has to come from the epoxide molecule. So we could do a split right here and make the 2 and the 3 be the start of the epoxide ring. So we would have to have some sort of organometallic group that would generate that carbanion, and then we could do the epoxide. So 2 and 3, and then we go to the alcohol there, the O there. That would be where the alcohol comes from. And then 1, 2, 3, 4. And let me double check my work. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so those could be precursors. But I also highlighted one in yellow. And so let's look at that one as well. So again, we draw our transform. Right? And in this case, this would be the 3, this would be the 2, and that would be the 1. And so we would need to divide it right there. Okay? And so when we did this, it'd be 1, 2, and then that right there would be the epoxide. And then we would need 1, 2, 3. So it'd be CH2, CH2, CH3. Would need to be the carb anion, right? So either these would be our two options if we didn't want to do anything else. Now, so this is where we kind of go back and we think about the starting material. So we've got some restrictions for the starting material. We need 4 or fewer carbons. So because this guy here has 1, 2, 3, 4, 5, 6, that doesn't really hit our that doesn't really hit our restrictions. So I would ignore the one in purple and go with the one in yellow here. All right, so if the screencast kind of broke up there, it's because I needed to group this so I could move this around. It was fighting with me. So you haven't missed anything. So we're still going to go with this particular synthesis because both of the reactants have 4 or fewer carbons. And so I just now need to write this in the forward direction. So I'm going to write that as a Grignard reagent. If you want to choose a lithium reagent, you're more than welcome to. And then I'm going to do an acid workup here. I'm going to choose HCl, right, as my acid to do the workup. And there we go. So hopefully this helps see how you can do a carbon-carbon ring opening reaction and add to your carbon chain. When we look at our next screencast, we're going to talk about the alkylation of alpha carbons and some control that we can take with thermodynamics, which can help us with some products.